In the last several videos, we've discussed code generation for a very simple programming language. In this video, we're going to take a look at code generation for a more advanced feature, objects. Fortunately, the standard code generation strategy for objects is really just an extension of what we've already learned. So everything that you learned before, we're going to be using, and then there's going to be some additional things that we do specifically for objects. And the important thing to know about objects, the slogan that you hear when people talk about object-oriented programming, is this one. So if B is a subclass of A, then an object of class B can be used wherever an object of class A is expected. So there's a substitutability property. If I have a piece of code that can work on A's, then it can also work on B's and any other subclass of A. Now, what this means for the case of code generation is that the code that we generate for class A, so the code that we produce for methods in class A, has to work unmodified for an object of class B. And to see this, keep in mind that when we compile class A, we may not even know all the subclasses of A. So those may not even have been defined yet. So in the future, some programmer may come along, define a subclass of A, and our compiled version of A will have to work with that new subclass. So there are really only two questions that we have to answer to give a complete description of how to generate code for objects. The first one is how are objects represented in memory? So we need to decide on a layout and representation for objects. And the second one is how is dynamic dispatch implemented? So that's the characteristic feature of using objects, is that we can dispatch to a method in the object, and we need an implementation of that. So to be concrete, we're going to use this little example throughout this video. And I'll just take a moment here to point out some features of it. So we have three classes, classes A, B, and C. Notice that A is a base class, and B and C both inherit from A. And all three classes define some attributes, some fields, and also some methods. Now, a couple of important features here is that notice that because B inherits from A and C inherits from A, they both inherit, both of those classes inherit the attributes A and D from class A. So these two attributes that are defined in class A are available in class B and in class C. So even though there's no mention of A and D in the definition, say, of class B, the methods in class B can still refer to those attributes. They are part of the attributes of class B. They're just copied over or inherited from A. Another feature of this example that I'd like to point out is that all of the methods refer to the attribute A. So attribute A is referred to in this method, in this one, referred to twice in this method, and also in this method. And the significance of this is just what we discussed a couple of slides ago. For all of these methods to work, attribute A is going to have to live in some place where all of them can find it when their generated code runs. So in particular, let's consider the method F. So the method F exists in all three classes. All three classes, when it runs, it will refer to the attribute A. And even though the objects would be different, in one case it might be running on an A object, in another case on a C object, it will need to be able to find the attribute A. And so therefore, the attribute A has to be in the same place in each object. And so how do we accomplish that? Well, the first principle is that objects are laid out in contiguous memory. So an object is just a block of memory, okay, with no gaps, and all the data for the object is stored in the words of that block of memory. And each attribute is stored at a fixed offset in the object. So for example, there may be a place in this object for attribute A. And in this case, it's at in the middle of the object, is in the fourth position. And no matter what kind of object it is, whether it's an A, B, or C object, in our example, attribute A will always live at that position, so that any piece of code that refers to A, any method that refers to A can find the A attribute. Now, the other thing that's important to understand, and this is a slight digression from what we're talking about, but it's a key aspect of code generation for objects, is that when a method is invoked, the object itself is the self parameter. So the self parameter is this entire object. So self, when a function is invoked, will refer to the entire object. So you think of self as being a pointer to the entire object. Remember that self is like the this variable or this name in Java. And then the fields will refer to particular, or the attributes of the object will refer to particular positions within the object. So for example, the A attribute we decided lived there. So here is the particular object layout used in COOL. So the first three words of a COOL object contain header information, and every COOL object always has these three entries. The first position is a class tag at offset 0. The next word at offset 4 is the size of the object, and then something called the dispatch pointer, and then all of the attributes. Now the class tag is an integer, which just identifies the class of the object. So the compiler will number all of the classes. So in our example, we had 3 classes, A, B, and C, and the compiler, for example, might assign them the numbers 1, 2, and 3. And it doesn't matter what these numbers are, as long as they are different from each other. So it doesn't have to be numbered consecutively or anything like that. The important thing is that the class tag is a unique identifier for a class. Each class has its own unique bit pattern that tells you what kind of class the object is. And the other fields here, the object size is also an integer, which is just the size of the object in words. And the dispatch pointer is a pointer to a table of methods. So the methods are stored off to the side, and the dispatch pointer is a pointer to that table. And we'll talk about this more later. And then all the attributes are laid out in the subsequent slots in some order that's determined by the compiler. So the compiler will fix an order for the attributes in the class, and then all the objects of that class will have the attributes of that class in the same order. And again, all of this is laid out in a continuous chunk of memory. Now we're ready to talk about how inheritance works. So the basic idea is that given a layout for a class A layout for a subclass B, so this is a subclass of A, can be defined by extending the layout of A. So we don't need to move any of the attributes of A. We can just add more fields onto the end of A's layout. And so that's going to leave the layout of A unchanged, which is a great property, because this is how the position of an attribute in the A object will always be the same for all the subclasses. So essentially, we will never, once we decide where an attribute lives in a class, it will never change for any of the subclasses of that object. So B is just going to be an extension of the layout of A. So let's take a look at our example here and see how that works. Let me just write down here a little bit about these classes because we don't have the example on the screen. So we had class A, and class A had 2 attributes, A and D. Okay, and it doesn't matter what their types are or what the methods were. Here we're just looking at the class names and the names of the attributes that are defined in the class. And then we had B, which inherits from A, and B added an attribute little b. And then we had C, which also inherits from A, but has no relationship to B. And class C defined an attribute little c. All right, so that's the structure of our example that's relevant to the layout of the objects. Okay, so let's talk about the layout of class A. So in position 0, at offset 0, there'll be a tag for A. That'll be some small integer that the compiler picks. There'll be the size of A. We'll come back to that in just a second. There'll be the dispatch pointer, okay, which we're going to talk about later. And then come the attributes of A. And they're just laid out. The way it's done in the COOL C implementation is that they are laid out in the order in which they appear textually in the class. So in this case, first the attribute A, and then the attribute D at offsets 12 and 16. And now, since the object, there were 2 attributes and 3 header words, that means that the size of the object is 5 words, and so it's a 5 that goes in the size field for A objects. Now let's take a look at B. Okay, so B is going to have a different tag. B objects will have a different tag, so they to distinguish them from A objects. There's going to be an extra field, so the size will be 1 bigger. But now the layout preserves the layout of A, so the attributes of A appear in the same positions, and you can think of there being an A object actually embedded inside of the B object. If I were to strip off the end here, if I were to just cover up this last bit here of B, I would see that this object here has the same size and the same attributes as an A object. And so any piece of code that could work on an A object will also make sense running on a B object. Now, of course, the tag is different because it actually is a subclass, and and there is this extra field, so the size is different. But the point is that any code that refers just to the fields here will still work just fine. So any A method that was compiled to refer to the methods of an A object will still find those attributes in the same place in the B object. Now, of course, there's also one more field here, which is the new attribute of B, and that just gets laid out after all of A's fields. So after all of A's fields come all of B's fields in the same order in which they appear textually in the class, and since there's only one, there's just one new field there. And now looking at class C, well, the story with class C is very similar. So C has its own distinct tag. It also has one more attribute than A, so it has size 6. And now, again, the A attributes are in the same positions, and now the C attribute just comes after the A attribute. And so notice here that A methods, again, will work just fine on C objects because the attributes are in the same places, and so the methods will find the attributes where they expect to. You cannot, however, call a method of class B on an object of class C, okay, because they have different attributes in the third position. These may have completely different types. It may not make sense to invoke a B method on a C object, but that's just fine, because if we look at our inheritance hierarchy over here, we see that B and C are actually unrelated. They are both subclasses of A, but they have no relationship to each other. B is not a subclass of C, and C is not a subclass of B. And so anything beyond their shared ancestry with A can be completely different in the layout. So more generally, if we have a chain of inheritance relationships, let's say we have a base class A1, and A2 inherits from A1, and A3 inherits from A2, and so on, with some class AN inheriting at the bottom of this chain after some long sequence of other intermediate subclasses. What is the layout of all these classes going to look like? Well, there's going to be a header, okay, the 3-word header, and that will be followed by A1's attributes, and then followed by A2's attributes, followed by A3's attributes, and so on, all the way down to AN's attributes down here. Okay, and if you look, again, something we talked about before, each prefix of this header is essentially a valid object, a valid one of these objects. So if I look at the first set of attributes, everything up to the end of the A1 attributes, that forms a valid layout for an A1 object. If I stop at the A2 attributes, I have a valid layout for an A2 object, going all the way from the header down to including the A1 and A2 objects. And then A3 includes all of A1, A2, and A3's attributes, and so on. Okay, and so each prefix of this object, of this AN object, has the correct layout for some superclass of AN.